All right, so Kirk, Stephanie, it's 10 p.m. Pacific time. It's whatever p.m. p.m. I think it's a.m. for Kirk. Yeah, let's
7.
get started with your 7 a.m. All right, sensible JVM configuration. Go for it. You start. See you later.
Yeah.
Okay, there we are.
Yeah.
Yes. So I think this is one of the talks that I wanted to put together for a while, I guess, just based on all of the things that I've encountered that we talked about in the introduction. And Stephanie had a whole bunch of other things I think that she wanted to put together. And so pretty much here it all is. I don't know if we have control of the settings to switch slides. There we go. Yeah, I think a lot of people are just really shocked at how configurable the JVM is, and just how many different ways you can configure it. And there's really more than 700 product flags inside the JVM, and they're in all kinds of these files called global files. So if you go and download the source code from GitHub, you can look for these global files and you can just pick them out. They generally fall into one of these categories, and the product, the one that you're going to use the most is going to be the product. There's some other experimental flags and things like that people sometimes use, but not very often. How do we flip slides here? There we go. So the question is really, how do we make sensible choices to which all of these flags, and which of these 700 are we actually going to use? And yes.
Sorry.
And yes. If you don't want to stay around for the whole talk, it's our spoiler alert. It's like the sensible JVM configuration is just to use default values, which is just to use none of them. And I always, again, try to look for some measurement or some motivation to use a flag. So you run into a situation, you'll say, okay, this is this situation, and you go screaming through the flags, trying to figure out, okay, is there any way I can configure my way out of this? And that's about the only time that I'll use a flag, and then I'll tend to document why that flag is being used, because very often what happens is in the next release, the problem you're trying to solve has already been solved in the code. So you need some way of backing out of these things afterwards. Yeah. Otherwise, we get into a situation which I term what's called like tune lore, which means, and this happens quite a bit. It's somebody's gone through, picked a whole bunch of flags, and for sometimes good reasons, sometimes not, but everyone's afraid to change them, right? And I think the most notable exception is going to be memory to this. Generally, you always want to understand how much memory you're using and then configure the JVM appropriately for that. So here's a case study. Hopefully we can go through this very quickly so you can get to the fun stuff, but I just picked this one randomly out of all the cases we had. So here's 26 flag set, and I looked at it and says, okay, this is fun. Let's just go through this and try to figure out what's going on with them. So I found deprecated flags that were default settings, and we said, okay, we can get rid of them, so let's just toss them out. Duplicated flags, and we can just toss them out. We have conflicting flags, or things that are saying two different things. So the last one wins, by the way, in case you're interested. So toss them out. And these ones cause all kinds of other issues. And, so toss them out. And by the time we're done, we start looking with these 7 surviving flags. And now what we're doing is just saying, are these flags that really should be used? And if they should be used, what are the values for, max perm size? Do we really need a max perm size setting? So this is a slightly older one. Excellent. Next. Sorry. So how should we approach this? Well, start with defaults, and then look at how your application is behaving. The tagline on measure, don't guess, and then change things as appropriate. And generally, we want to change things one at a time. Java heap size, number of helper threads, and things like that. And I think Stephanie is going to run through.
Yes. Yeah. So in doing that, right, if our first step is starting from the defaults, we have to know what even are these defaults, right? So if you're using JDK 8, which I hope you're not, because you should be upgrading your Java, but I'm sure you are because everyone still is, you are using parallel GC by default. And then if you're using JDK 11 plus, you are probably using G1 GC by default. Unless you have less than 2 CPUs and a small amount of memory, then it will stick you with serial GC. And then regardless of which version you're using, 8 plus, your helper threads will be equal to the number of cores you have if you have 4 cores or less. And then once you have 5 or more cores, the threads will be 5/8 times the number of cores. So say you have a machine with 16 cores, that's going to give you 10 helper threads. And then your initial Java heap size will be 1/64th of the memory on your machine. And then the max heap size will probably be 1/4 of the memory available on your machine. Unless you have a smaller machine, then it will give you half of the memory on your machine. And we can see these flags right here. So if you're interested in the source code in JDK 8U, they live in globals HPP. And 11U and TIP, they're all sectioned out into GC globals HPP. So we can see, max RAM fraction, initial RAM fraction, all of these can be used to set your heap size. And so when do we want to change this? Right, the big thing is really we want to use less memory because we want to spend less money, right? Memory drives the cost of computing in the cloud. So if you want a bigger machine, you're going to have to pay for that bigger machine. And we would all rather not do that. So if you're paying attention to one part of this talk, here's how to save money, right? And the memory that your system has is not at all correlated with the amount of memory that your application actually needs, unless you as a programmer made the decision to use that machine, right? And as we saw, Java is setting all of your default heap sizes just based upon the size of your machine, which may or may not be accurate. It probably isn't. And let's say you're running in a really big container. Java is perfectly happy to just keep on increasing your heap size because it doesn't want to perform garbage collections. And then you could end up with a lot of space between your maximum heap size and your actual live data set. And if we're wasting that memory, we're wasting that money. And especially in containers, older versions of Java, so another plug to upgrade from JDK 8, we're not aware that containers were a thing that exist. So I could be running on my massive host machine and this little container, and Java's like, great, you've got a lot of memory. I will happily use 1/4 of your memory for my heap size and just size it up larger than the container is even allowed to be, and your container will get killed and you will be sad and you should upgrade your Java. Although actually a lot of container support has been backported to later versions of JDK 8. So that should not happen, but we still don't want to be wasting memory. So the heap size, should really be set based upon your live set size and your allocation rate rather than what machine you happen to be running on. And the heap is made up of the 10-year generation and the young generation, assuming we're using a generational collector. So G1 would be your default in 11 plus. And it would be pretty reasonable to set the tenured space to about 2 times the tenured occupancy or the live set size. And you would know this because you started with a run with nothing, right? Just as a baseline. So theoretically, enable GC logging flags, you now can figure out your live set size. And even just this is a pretty solid starting point. By default, the JVM will set the tenure space to be 2/3 of the heap size. So if we want our tenured space to be twice the tenured occupancy, just set heap size is 3 times my live set size. So you can use XMS is your initial, XMX is your max. Let the JVM do the rest. Like, I have made a decision based upon my application and not just my machine. This seems reasonable. And it probably is, because JVM ergonomics are pretty good. But if you do want to keep going there, and size the young generation as well, the young generation is made up of Eden and survivor spaces. So you can set your size of Eden to accommodate your allocation rate, let's say with a GC frequency of every 30 seconds to a minute. So if I'm allocating at a rate of 1 megabyte per second, which is a dumb number, but it works for this, then I would have a 60 megabyte Eden to accommodate a GC frequency of every 1 minute. And I could start sizing my survivor space, say my survivor space is the same size as Eden, and then make these changes, and then you can iterate, okay, do I get premature promotion? Do I not? Where is my application doing well? Where is it not? And then you can resize these things. But by default, the JVM will do ergonomic sizing and should do a pretty good job at figuring out these sizes for you. So again, even just setting your max heap size based upon your live data set is a pretty reasonable place to start. So then this is how you would actually go about getting that information, a graph of tenured occupancy after GC, which if Kirk has any input, because he's the king of garbage collection graphs, but we can just see occupancy is on the y-axis over the runtime. So then you could figure out, okay, what is my tenured occupancy? What is my live data set? What heap size is reasonable for this application? And how consistent is that? How consistent is that? Do I want extra space just in case I have bursts, or is it fairly stable? You can make those decisions. Same thing with your allocation rate. This is just allocation rate on the y-axis over runtime, figuring out, okay, what is a reasonable size for your young generation and Eden to be. So we want to use less memory, and then we also want to use the right amount of threads. This is especially true if we have multiple processes running at the same time. So ideally, right, the number of threads that we have is more or less equal to the number of cores we have. So back to the default settings, right? If I have a 64 core machine, the JVM will get 40 helper threads, because that is 5/8 of the number of cores, which is fine. 40 helper threads, 64 cores, I can run, seems fairly reasonable. What if I add 10 Java processes on this machine? Same 64 cores, they all get 40 helper threads, and now I have 400 garbage collection threads. Maybe this is not so great, right? I can't have 400 threads active at the same time on my 64 core machine. So we can use the active processor count flag to adjust that and say, okay, I have a 64 core machine, but I'm going to pass active processor count. Maybe I give each process like 6 cores, so that way they're not all fighting for those. But we really want number of active threads equals number of cores. So the caveat here is if not all of my threads are active, maybe this is actually fine. Right, so if I have a synchronous process, say my thread does something for 1 millisecond, I access a database and I wait for 100 milliseconds. If all my threads are doing that, maybe I can have 400 threads on 64 cores, because most of the time my threads aren't actually doing anything, and maybe that's actually a better use of my resources. But if I have an asynchronous process and all of my threads are working at the same time, 400 threads, 64 cores is not going to work. So based upon how much CPU do you want to be using, what processes are you running, make those decisions that the JVM cannot make for you because it doesn't know what else is going on. Yeah, I mean, this is pretty much the summary of it all. That went faster than I thought it was going to, but start with the default settings and then measure instead of guessing, right? So set your heap size based upon your allocation rate and your live set size. You can go down the rabbit hole with sizing your survivor spaces and all of those things, but even just setting an overall heap size and letting the JVM figure out the rest is better than letting it just use the amount of RAM you have. Same thing, set your active processors based upon the amount of active threads that you have and what else you're running. And then if you want to get crazy, you could choose a different GC. You know, G1 is the default, but ZGC, some of us call it ZGC. I said I wouldn't say ZGC, but I have to be inclusive. Kirk is the one that says ZGC. But that's a pretty good option. If you really hate pauses and you can only tolerate 10 milliseconds and 11 is too much, maybe you like Shenandoah, but maybe you also don't care about throughput, who's to say? That could really be a whole nother talk on which GC to use. Generally, G1 also does fine. But yeah, and if you wanted to dive deeper, there are millions and millions of flags that you can go really dive into. And, you know, they're all on GitHub, but if you just want your application to run properly, I would do not that. Stick with heaps and you'll be okay. But it's pretty much all I got. Sensible configurations are the default ones. It's short and sweet.
Yeah, that's generally the case. We just want to pick flags that help us understand, or well, help the performance. And you know, GC ergonomics work quite well in most cases, but sometimes you just need to give it a helping hand. You know, the thing about trying to size Eden for the allocation rate, that can be tricky business, because what happens is that the garbage collector itself will have a direct impact on the throughput of your application. And so what you're going to find is that as you slow the collector down, the allocation rates are going to go up. So sometimes it takes a couple of rounds of tuning to actually find the sweet spot for the amount of memory that you need for your application, because what you want to do with generational collectors is you want to prevent short-lived data or transient data from ending up in the tenured space, where it's typically more expensive to collect that. The more expensive to collect means that you have higher GC throughput, which means you end up having lower application throughput. So there's this fine balance that you're trying to achieve when you're configuring memory, and you know, as you change the settings, you're going to change where this balance is, and sometimes, you know, you'll change it a bit and it'll get better. Sometimes it gets worse, but generally the data will say, oh, it looks like you're going in the right direction, but you haven't gone far enough to solve the problem. So that means that you'll look at the data again and you'll say, okay, well, let's keep going in this direction. And you can often end up in configurations that you wouldn't expect to see. For instance, if your allocations are high enough in your application and your live set size are low enough in your allocations, then we can often see that the default configuration of having a small Eden and a large tenured is not what you're going to achieve. You're going to end up with a large Eden and maybe a small tenured size. But since both of these memory spaces play different roles, and you have to use this different tuning strategy for both of them, and then throw them together, and then you know, I'd strongly recommend using the max heap size in this case, right? Because this really isn't about how much memory you want to give your application. It's generally about how much memory that your application needs, which I think Stephanie said a few times at the beginning. And generally what we find is that people especially when you get into container environments, will end up starving their application either for memory, or strangely enough, they'll end up starving their application for threads. And in both cases, you want to try to scale in the right direction so that you have enough resource for the application. Either generally that's from what we've seen, it's a scale up situation, right? And then once you have enough resources for a single process, that's when you're going to want to try to scale out. In one case recently, we had to go in the opposite direction with memory. So they had allocated, surprisingly, about 8 times the amount of memory that they needed. So then we could scale down in that case and then have them scale out. And so it's really, in that other case, they had taken some measurements, but unfortunately they weren't able to interpret them properly. And so they scaled up memory, but that caused them to do other things, which solved the problem. So it's sort of like they did the wrong thing and got the right result. So it's sometimes tricky business, and I think that sometimes it's just it can be really worth the cost to bring someone in who specializes in this, just to give you a helping hand and hopefully leave you being a little bit more knowledgeable of what's going on in these cases, and then and then that's information that you can take forward and use as you continue to sort out how to configure your applications when you're deploying them into production environments. Do you have anything to add to that? I think we're done.
I mean, pretty much. I don't know if we have a Q&A with Bruno or...
Yeah, you can bring Bruno in here.
Yeah, I can totally ask questions, because this is a topic that it is very close to my heart, and I think my primary question is this, right? Default JVM settings. Most of them, not most of them, but many of them that have these impacts in memory and garbage collection, they were set before the explosion of containers. Many of them were designed for a deployment model that today is not actually the norm in the cloud anymore. So my question to you is: should we expect to see more research from your team, but also from different teams outside Microsoft, like Red Hat and Oracle and those systems and other companies, in this area of like what should be better defaults for the JVM considering container-based deployments?
I personally have always believed that the default settings, especially for memory, for threads, it's been relatively reasonable. And having it adapt to containers is the right way to go. There's a couple of flags we didn't mention here just because we didn't want to pile on the flag settings, but I think the default settings for memory rarely work for applications. They've rarely worked applications. They were made on a bunch of assumptions, probably 2005, and I don't. Those assumptions have been challenged that much. Certainly, containers have challenged them. I'm not sure that the response has been appropriate, and I think there's work that we can do to actually make the JVM more container friendly. The other idea I think that's here that I think was pretty foreign to people when they were first originally creating these garbage collections is the idea that you would tune bases separately, and you end up with a single configuration max heap size, and then everything gets proportioned out because of that. And applications are all so different. They have different memory pressures, and you need to be able to adapt to that particular memory pressure. And some of the heuristics inside the JVM that would cause that adaptation are yeah, I've actually had demo failure expecting the JVM to do something and it doesn't, simply because of which quadrant of memory it's been laid out in. And so there's weird timing heuristics that can, you think you're getting a certain behavior and all of a sudden you don't, you get a completely different behavior. And it can make a real difference in the one case. I can cite, like when we forced a particular configuration on the JVM CPU for that application about 20%. Prior to the CPU was running quite hot, about 70%. And that change simply came from getting the JVM to adapt to the load properly, and so there was a little configuration that needed to be done to do that. So yeah, I think that there is much we can do for the settings to make it worthwhile. I mean, the original settings on the fact that we were trying to share a machine. With a virtual machine, you're not trying to share it. You're trying to consume the whole thing. So just that one assumption alone is enough to break the default configurations for memory.
Right. And the other thing that I was thinking, and I wanted to ask you, is like, should we expect to see a garbage collector in the next 5 years that is designed for small heaps? Because we see a lot of advancements in garbage collectors in the JVM for large heaps, with like
we have one
below 1 millisecond.
We have one.
What is the latency? Garbage collector latency, and developers. First of all, developers actually don't know the defaults of the JVM. They just make some assumptions. Oh, the JVM will set magical configurations and figure it out, but there are some defaults depending on the resources. And I wonder, like, what do you think will happen in the next 5 years or whatever time, like with this debates about small containers? Do we expect, number one, do we expect to focus in garbage collection for small heaps, like below 1 gigabyte of memory, or at most 2 gigabytes of memory? Do we expect changes in that, or is it something that, nope, what there is, it works fine?
Well, I think we have collectors that have low latency with small heaps. The serial collector, exceptionally efficient, right? It's just single threaded. So it never worked for large heaps, but for small heaps, it's incredibly efficient. It's full stop, which means you don't have these things, the barriers in there, and every time you want to write a concurrent collector, you have to have some form of cooperation between the mutator threads, application threads, and the garbage collection threads. And this happens in these GC barriers. You get to a C collector, it's full stop the world. I don't need any cooperation. Cooperation is I'm working or you're working, we're not working together. And so you get exceptionally high throughput in that environment. And in small heaps, it's going to go very, very fast because it's not trying to do every time you parallelize, you take on overhead. So it's even better than the parallel collector because there's no overhead of parallelization in there. Now, can we do better? I think the thing is we can. We probably can. I was talking to the generational, should I say, ZGC guys on Monday, because they're here in Stockholm, and they're looking at smaller heaps, and they would like to port smaller heaps with ZGC. Are they going to be able to do it? I think so. I just think that the overhead on having a concurrent collector like that is going to probably prove to be much higher than we want to accept for these type of applications.
Okay. So that's an interesting challenge, and I bet Stephanie would like to have fun on those challenges. Right, Stephanie? Is that something that you feel excited
Yes.
about?
We'll see.
All right, awesome. All right, Stephanie, correct. Thank you so much for your presentation. This is great stuff. As I said, this is a topic that I am very passionate about, and I will catch up with you later offline because I think we all work for the same company, I guess. So have a wonderful night, Stephanie, and drive safe home. And Kirk, have a wonderful day in Stockholm, and enjoy all the rest of your days. And thanks for being part of JDConf 2022.
Thanks for having us. Yeah. Have a good
Thank you, Bruno.
whatever time of day you all are at.
All right, so I'll cut you off now. So bye bye.